Neil deGrasse Tyson here, your personal astrophysicist, and guess where we are? The Jet Propulsion Laboratories of the California Institute of Technology, Caltech. This is one of the branches, one of the 10 centers of NASA scattered across the country. This one is in Pasadena, California. So we're here at Charles Elachi Mission Control Center. He's a former director of JPL. I remember him. And we have the current director of JPL, Lori. Oh my God.
Good to see you.
But we go way back.
Way back.
Way back. I remember when you were.
Just a baby scientist. What do you think of our little place?
I love what you've done with the place.
Thank you. It's really special. This is we call it the center of the universe.
Yes.
Everything happens right here.
Right.
From all over.
Right. Is this also the place where Europa Clipper data arrive?
Yes, this is it. This is where we talk to all our deep space missions, and Europa Clipper is the
It's
latest.
not just the latest
It's
one.
the
Just
latest
put it in the list,
Right.
and there it is.
Oh, it's so important though.
And I understand
Everything's good.
it's going to do at least 2 gravity assists, so
It is.
that's a thing.
Mars, flyby, and then come back around, swing by Earth, and then see, we're off to Jupiter.
Now, in the past, we've done Venus flybys as well, so why not Venus for this?
So this one, the trajectory we've had has been worked on over many years, and that is
Top people working on a trajectory.
We literally invented deep space navigation right here at JPL.
Okay. And so what you got here?
So this is one of the most exciting new spacecrafts, the Europa Clipper spacecraft. At about, I think 1/5 scale, Europa Clipper, when it's got its solar panels open.
And it looks like you have one
panel's
panel
open
to the right, and the others is accordion
Yeah,
over
that's
here.
the way in launch configuration. That's how.
So it would be out like this.
That's right. When it's fully extended, that's about 100 feet.
Wow.
Which
okay.
is basically a professional basketball court.
And you especially need them that large when you're going that far from the
Exactly.
sun. Yeah. So tell me, where are you sending this?
So this is going to Jupiter's moon Europa, and
We love Europa.
ice-covered moon with
We
a
love
global
Europa.
liquid water ocean,
Yeah.
great place potentially for life to be living today. So the main question that this spacecraft and all of the instruments are working in service to investigate is whether or not Europa is habitable. We have really good evidence from the Galileo spacecraft that Europa has this liquid water ocean. But we don't yet know, does that ocean have the full suite of elements that are needed to build life? And does Europa have...
Elements, you mean the chemistry?
The chemistry,
Yes.
right. You know, your carbon, oxygen, nitrogen, phosphorus, sulfur. Life on Earth takes about 54 elements from the periodic table. So we want to do an inventory of that chemistry.
Life as we know it.
Totally.
Yes. Okay. Just to be clear.
So one really cool thing about the design of the spacecraft here also is that in other spacecraft designs, like with the Galileo spacecraft and the Cassini spacecraft, there was always kind of a tug and pull between the different instruments and who got to look at what when. This spacecraft is going to be orbiting Jupiter, and it will fly by Europa some 45 times. Some of the closest approaches are going to be about 25 kilometers above Europa's surface. Think about that. That's insane. That again gets at like how brilliant the engineers are, where, I mean...
Well, wait, so it's fundamentally orbiting Jupiter, not Europa.
That's right.
And you're just having clever orbital dynamicists
Pinball wizards.
Pinball wizards. I love it. Skim the surface of Europa. That's where you get your best data.
That's exactly right.
Yeah.
And as we're coming in on close approach during those flybys, this side of the spacecraft is going to be looking down at Europa. And so the cameras and the various spectrometers will be collecting data all the way through. And then on the front end there, what we call sort of the RAM direction, we've got some mass spectrometers that will be collecting stuff that, say, is coming off of Europa's surface or ejected from the ice if there are cracks and plumes erupting. And so all of the instruments will be collecting data throughout the flybys. And it's just going to be astonishing. Like the pictures alone, it's going to take 6 years for this spacecraft to get out there. The pictures alone, your jaw is going to drop to the floor.
Will this require a gravity assist?
So we're going to do a Mars gravity assist, an Earth gravity assist. Thankfully, not a Venus gravity assist, because going close to Venus presents all sorts of thermal challenges. Also on the panels, you see these little antennas sticking out.
Yeah.
That's part of the ice penetrating radar that will send waves down into the ice.
So you're doing double duty on the
Solar
solar panels.
panels.
Very clever.
Exactly, yeah.
Right, because I was going to ask, if this does close flybys and it has all these cameras and sensors, your water is still very deep under the ice. What the hell are you looking at? All right.
And that's where the magnetometer, the ice penetrating radar, and the gravity science of the spacecraft itself, right? When you talk about galaxies, et cetera, you're talking about massive gravity wells. Well, even a tiny moon like Europa, which is about the size of our moon, creates a little gravity well. And so as Clipper is flying by Europa, it's going to accelerate a bit and decelerate a bit, little redshift, blue shift as we're transmitting signals back. And from that, we can figure out the moment of inertia of Europa and get at the interior structure and mass distribution. So there's all—
And that's a whole other team.
It's a whole other team, yeah. Each of the instruments and investigations has got a team.
Right, because it's one thing to dig in there and see where the mass is distributed. It's another thing to have that distribution of mass affect your trajectories. So that's like a sneaky way to get in without actually digging in.
That's exactly right.
Yeah. Oh yeah, the Europa Clipper. So Kevin, where are we now?
We are in the Ocean Worlds lab.
I love it.
And so, by Ocean Worlds, we mean, of course, the Earth, with the ocean that we know and love and need to protect, and we do some work on Earth's ocean. But then we've got these worlds like Europa in the outer solar system that are covered in ice, and beneath their icy shells, we've got these oceans. Now, in our lab here, we've got all this fancy machines, these thermvac chambers, where we can recreate the surface conditions of Europa. We can replicate the ice and—
To the extent that you understand them.
That's right. We do experiments based on older data. Those experiments inform future missions and so on and so forth.
And I guess you tell this looks mad scientisty. I just want you to say.
So this is—
Wait, can I turn some of these? Can I just?
the pumps are off right now, so yes.
Okay.
Go ahead.
No, no. I'm not touching a thing. This blows up. So all of this, I mean, who would have thought that you would need this much hardware to simulate something in the solar system?
That's right. And so the reason that we need this much hardware and all the pumps and everything, Europa has no atmosphere. I mean, it's got a whiff of an exosphere, to be correct, but it basically has no atmosphere, so it's the vacuum of space.
So you get that, check, all right.
Pump it down,
Next.
and then we're at 100 Kelvin, or minus 280 degrees Fahrenheit.
So cool it down.
Super cold.
Pump it, cool it, all right.
Pump it, cool it. And then Europa's surface is bombarded by a hailstorm of electrons and ions and protons.
He doesn't literally mean hail, okay?
That's right.
Hail, did they tell you this? Hail is something else, okay? Okay. A flux of, okay.
Yeah, exactly, yeah,
okay.
or fluence. And so—
So stuff coming from the sun, solar wind.
No, it's a little bit of solar wind, but Jupiter's magnetic field entrains stuff coming out of Jupiter's atmosphere. And think about Io. Okay, Io is the innermost large moon, and Io is the most volcanically active body in our solar system. The stuff spewing out of Io, predominantly sulfur, gets turned into sulfur ions, and that bombards the surface of Europa.
Wait, so you're telling me the volcanic eruptions on Io achieve escape velocity?
And then they catalyze chemistry on Europa's surface.
So it pollutes the environment of Jupiter.
That's right. Or the sulfur from Io may actually help make Europa's ocean habitable.
Ooh.
Volcanism on one moon, feeding life on another moon.
That's deep.
Deep in there, replicates the surface of Europa. The best place to find Europa on Earth is inside that.
Inside this vessel.
Yep.
Now, you don't buy these parts in a catalog.
You kind of do.
You can?
Yeah. You do some custom orders on the various shapes, but a lot of these companies, they provide a catalog and you just order the parts.
Wow.
It's like massively grown up Legos.
So Kevin, this looks like Europa 101, is that right?
In cross section.
A cross section here. And it looks like you've got heat sources down here to make vents. But let me ask the geologist, because you're the astronomer, why would we think that Europa would have heat sources inside?
Europa would be a little bit unique compared to the Earth, where it's residual heat. On Europa, it's the orbit around Jupiter that causes some stresses.
And a source of energy that melts what would otherwise be ice all the way down.
How the heck could an ocean exist that far out in the solar system?
It's way outside the Goldilocks zone.
But it's not energy from the sun, it's tidal energy just providing the mechanical deformation, the friction, the heat. And it may be strong enough to power hydrothermal vents. Here we've got perhaps a chemical gradient that life could harness on the seafloor. With Clipper, we're going to be observing the surface of Europa. Here, the orange-yellow spots, these, I think we've got really good confidence now, are salt deposits, and in some cases, sulfur deposits from Io. But the window, or the ice of Europa, serves as a window into the ocean below.
So this would be evidence that this is a salty ocean, provided there are cracks for this to creep up and manifest.
Exactly. And we still have a lot to understand about the geology of those cracks and everything. And so one of the key challenges is, how do we separate out the exogenous stuff, the micrometeorites, from the endogenous stuff, the stuff coming from the ocean? I think with experiments...
And there's some clear sort of dividing line here, right?
Yeah, so this is one hypothesis for how the ice shell works, where it's got a thick, sort of ductile component to the ice shell, overlain by a brittle, thin ice shell. And so one of the key questions that I'm particularly interested in is, yeah, we've seen the salt spectroscopically on the surface, so we know that material is coming up from the ocean. Mixed in with those salts, or coming out of any plumes that we find, might there be carbon compounds? Might there be organics? Might there be any whiffs of life below?
So you get to know the chemistry down here without actually having to
Exactly.
to cut a hole.
That's right.
And go down.
That's right.
It is beautiful. So stupid.
So this chamber, which we endearingly call the Ark of Europa.
That's why there's an Indiana Jones reference right here. Okay.
With those other chambers, we are replicating the surface chemistry. There's another question that's interesting when you think about the surface of Europa, and that is, what is the shape of the ice? At the large scale, it's fractured and cracked by the tides. At the small scale, there's no wind or rain or anything on Europa. And so at the kind of meter scale, it's all about sublimation, okay? Water molecules just popping off into that vacuum of space for the most part.
So just so I understand, when we think of ice colloquially, there's only one kind of ice. But chemically, you guys know of ice manifesting in slightly different structures.
Right, although I would say geologically. Chemically, it's still H2O.
Yes.
But from a mineral standpoint.
Minerals, how it assembles into a crystal.
That's exactly right. Here we're doing ice 1H predominantly. And then this bar here, that simulates the sun, and it can raster back and forth, simulating the diurnal cycle that the daily Sunday night, the day-night cycle.
Whatever the day is on
exactly,
the
which is about
world you're thinking about.
That's right. For Europa, it's 3.55 Earth days.
Okay.
And so this light bar goes across over that time.
And you have accurately reproduced the full spectrum of the sun.
The photon economy.
Including the UV and the visible and
we don't go
infrared.
so far down in the UV because it gets a little dangerous down there.
Okay.
But in terms of heating and looking at sublimation-driven erosion, that's what we can do in here. But so let me show you something else. Let's go down to the bottom of the ocean, not Europa's ocean,
not yet.
but Earth's ocean.
Okay.
And so that'll take us into the green monster here. So these rocks, many of these rocks here came from various hydrothermal vents on Earth. So these
are from deep submersibles going to the bottom of the ocean.
Yeah, so these are rocks and some of the chemistry that drives life in the deepest, darkest depths of our ocean, and may well also represent analogous systems on worlds like Europa. Or
that looks like a hunk of salt of some kind?
That was actually carbonate.
Carbonate, okay.
From Lost City in the Atlantic.
So it's like limestone?
Limestone is more kind of metamorphosed, higher temperature pressure.
Okay.
So this is kind of like freshly precipitated.
I see. Okay.
Carbonate. So take a whiff of this. That's what the origin of life might smell like. A little sulfury, a little nice bouquet.
Something might crawl out of here one day. If Ziploc only knew how you were using their bags.
Many layers. So now we are in another part of our Ocean Worlds lab, but here we're focused on robotic systems and instrumentation to explore Earth's ocean and cryosphere with an eye and a bridge towards someday flying things like our buoyant rover for under ice exploration on a world like Europa.
So we got authentic engineers here.
That's right.
That's what you're talking.
So scientists, we come up with the crazy ideas.
Right.
Engineers are like, wait, we got to build that? And,
Right.
And so that's true with Clipper. That's true with this amazing robot that we call BRUIE, short for
BRUIE.
Buoyant Rover for Under Ice Exploration. On Earth, life loves these chemical gradients. One chemical gradient that's of great interest, geologically, biochemically, et cetera, is the ice-water interface. And that could be true for Europa also. There might be life at the bottom of the ice shelf.
Right there.
Right there, exactly.
So when would this fly?
So this would not fly to Europa for decades and decades to come. But in the meantime, we're preparing to take it up to Alaska, to put it under ice in Alaska and study methane coming out of the permafrost. And the basic idea of this vehicle, so these wheels, if you want to hold this, you can be careful, it's spiky and sharp.
This looks dangerous. It looks like a ninja wheel.
It's spiky to get grip on the surface. So this chassis here floats. And then, here at JPL, we're really good at making rovers, Mars rovers, et cetera. This is an under ice rover. It thinks that the surface is the ice. And then with its two wheels, one of which you have, it roves along the underside of the ice. And this tail has instrumentation, and this is kind of what we call a torque tail to allow it to drive forward or backward, and then image what's
So it's
happening.
floating.
Yeah.
That gives it its position
Yeah.
in the vertical depths of the ocean. And because it's floating, it has buoyancy, it'll put pressure on these spikes up against
That's exactly right.
the ice that's there.
Welcome, Neil.
Yes, thank you.
All right.
Thank you.
So,
You're the eel man.
Oh, I'm not the eel man. This is the eel team.
The eel team.
I am one of them.
One of the
One
eel
them.
people.
Yeah, exactly.
Okay,
One
good.
of many eels people. Yes. So our dream is to enable exploration of subsurface ocean of Enceladus. There are natural opening of the ice.
There is?
Oh yeah, of course. There's a crevasse.
Okay.
Which is the
So
vapor.
on Enceladus, you're not going to go dig a hole.
No,
You're going to use a hole
you
that's
don't
already
have to.
there.
Exactly, that's the point.
It's where these
We
vents are coming out,
explore-
I guess.
Yes, it's like they are inviting us.
Oh, this
the
calling-
door is
calling
there.
to us.
Exactly,
Okay.
right? And it's just 9 AUs away.
Yes,
right? So
okay.
why not?
It's our backyard.
Backyard, yes, our backyard. What we conceive is a snake robot,
Okay.
right? Called EELS, Exobiology Extant Life Surveyor, that gonna land on Enceladus, explore the surface, finds the best entry point to the vent, go down all the way to the ocean.
The sub-ice ocean.
Exactly.
Yes.
Where we can find life, maybe.
So what would be a sign of life? Something swimming up saying hi? Or you're going to do chemistry and maybe find microbes?
That's a great timing to invite our science read, Morgan Cable.
Hello. Okay, good,
Great
good.
to meet you.
Good, uh-huh.
We are hoping to include a variety of payloads that could both look for chemical signatures of life as well as potential morphology biosignatures. Those would be like cells or bits of cells, and potentially some metabolic indicators as well. If we find food or things that microbes have left behind, those would be the types of biosignatures we'd look for.
So what's the largest organism you would conceivably find? Because on Earth, we went billions of years with just microbes.
We did.
And only later did we get big. So, but that's been around for billions of years as well.
It's a great question. Typically, we look to examples of Earth, as you know, to try to model and give guesses of what might exist. And for us, for places like Enceladus, we look to hydrothermal vents down at our seafloor. There, you see more than just microbes. We find rich communities that include, shellfish and
Right, crabby-looking
octopus.
things. Yeah.
And those, what are those? Those tube worms. Those can live to be 200 years old. Did you know that?
No, I didn't know that.
Amazing.
Okay. All of those capacities to test for life, are they going to be built into the eel?
That is the idea, that each module of EELS could include a science payload, or it could include other things that the robot needs to move and sense its environment.
Wow.
We're not there yet, but with extra few billion bucks, yes, we can.
Oh,
So we built the robot, right? Built the robot and brought to the place that is closest to Enceladus.
And where's that?
It's glacier, right?
Oh.
The Athabasca Glacier in Canada. We went there exactly a year ago. We tested on ice, but then we tested in a crevasse. So 2 arms, right? Expand the arms like this, push the walls against each other to support its own weight, like shit, and use the screws to go down or up.
Oh, because it's not neutrally buoyant here. So otherwise it would just fall and get stuck.
There's no water.
So you control, I like that.
It has to support its own weight.
Yes.
There's a jet coming out, right?
Right.
And this is how happy we were when we made.
Look at that, everybody. Okay.
All right, you want to see it with your own eyes?
Oh, you have a real version of one.
Exactly.
I've only seen pictures.
Right behind you.
Okay, that's a little creepy.
Yeah.
I'm gonna have nightmares of this thing turning and chasing me down the street.
Mildly terrifying.
It won't bite you.
It doesn't bite?
So it's controlling itself. Mike Patton has basically asked our robot to come here, and the robot has woken up. It has no idea what the world looks like. It's getting live data from its sensors, and it's making decisions about what's traversable.
You can say it, it's AI, just say it.
It's AI,
Okay,
exactly.
fine.
Right now in our Mars rovers, if anything goes wrong, we just brake and ask home for help. But on Enceladus, when you're going down into the vents, the plume forces are constantly pushing you up. So you need to push into the walls with sufficient amount of
To grip.
force to grip so that you don't get blown up. And the robot is solving that problem in real time.
Can it go sideways?
It can. We'll actually invite you to drive the robot yourself.
That's a little scary for me. It looks like it's assessing who we are. So how long realistically would this be? About this length?
For the eventual Enceladus mission, it would be roughly this size, but it's modular. It's like one modules that repeated 11 times.
Very scalable.
Yes, according to the mission. If our destination takes a decade to reach, you don't want to wait for a century to get the right science, right? So the whole point of EELS is versatility, so that you can directly explore these unknown environments in one shot.
Easy.
First mission. The big challenge is you have to deal with a lot of uncertainty because you're going in the unknown and you're very limited in bandwidth in terms of communication. So there's a lot of need for AI. So once you land there, the robot cannot just live stream all the video data. So it needs to have a lot of reasoning to make all the decisions on its own. So Rob is going to show how we've integrated a VLM, vision language model, to bring some of these reasoning capabilities to the robot. Hey, EELS, can you go ahead and introduce yourself?
Hello, I'm EELS, the extant exobiology life surveyor. I'm a snake-like robot designed to explore planets and moons, especially Enceladus. My mission is to navigate tough terrains, collect ice and water samples, and look for signs of life. I move using screw-driven modules and have various sensors to help me navigate. Right now, I'm at NASA's Jet Propulsion Laboratory, preparing for my mission. My operators, a team from JPL, control me remotely. If you have any tasks or questions, just let me know.
Go ahead and scan the room. So this is now getting to that action part where there's an online agent that's running, getting commands from ChatGPT and like talking to the command center.
So scanning the room is the full 3D space.
You're going to see it pop up here on the screen soon. It's using LiDAR. And it's constructing a map of everything it could see in here.
We call that Cobra pose.
I love it.
We're going to tap into the onboard sensors like the camera, and we're going to have EELS describe what it sees in the room. All right, EELS, go ahead and describe what you see in the room.
The room has several people working around tables and equipment. There are computers, monitors, and office equipment. Key points. People are 3 meters away. A desk is 4 meters away. A monitor is 3.5 meters away. A cable is 2 meters away. And a black box is 1 meter away. Let me know if you need more details.
Can we ask it if it sees anything alive?
Oh, good.
Yeah, we can.
Good.
Do you see anything that's alive?
Yes, there are several people in the room gathered around the table and engaged.
So we detected
Let me know.
We found